So today the thing I wanted to talk about is differential equations, which is honestly, the title here is going to be a little misleading. You could do a doctorate on differential equations. It's an incredibly huge subject. It's very, very important. Um, so I'm sure a handful of you have kind of gotten to the point where you realize that your very first course in physics, the one maybe you took in high school, or if you took an algebra-based physics course in college, they kind of lied to you, and they told you that you could do physics with algebra. But secretly, a lot of the stuff you do in physics is actually calculus. It's just that they sort of they hide the calculus. They give you the equations that are derived from the calculus, and you kind of assume that, like, oh, the acceleration is constant or the velocity is constant. There's no changing things like that. When in reality, a lot of that stuff you have to do using derivatives and integrals. You have to compute them using physics. Hence the term calculus-based physics for a second course in physics, usually the college level course. Here, our calculus-based physics class is our like Physics 111. However, there's a third level actually. It turns out that just saying physics itself is calculus is kind of also a lie, because really what you want to do to be able to do physics is what's called differential equations. And differential equations is kind of an application of calculus. It's a it's a sort of an entire subject that you need calculus to be able to understand. It really is one of the reasons why you need to learn calculus in order to be successful in a lot of fields, because solving differential equations is one of the most important applications of calculus. So what is a differential equation? Well, a differential equation. So a differential equation or a uh, or a diffie q is an equation that relates a function to its derivative or derivatives. In other words, it's basically what you set up an equation that has some function and some some function of that function's derivatives. For example, y prime is equal to y. All right, this is a very simple differential equation. It's looking for the function y. So y is a function of x. And we're looking for the function y as a function of x that is equal to its own derivative. Right? This is what we would call a first order differential equation. Because it only involves the first derivative. The order of a differential equation is basically what's the highest derivative that comes across. The order of a differential equation is kind of like the degree of a polynomial. And actually there's a lot of ways in which you can use the theory behind polynomials to effectively study differential equations. We will not be talking about that at all. That is for like a real course in differential equations. We're sort of just scratching the surface. So, before we actually talk about like the method that we're going to be able to use to solve a differential equation, does anybody have any ideas what the solution to this differential equation is? What's the function y such that y is equal to its own derivative? Any guesses at all?
It has to do with something with the e.
Yeah, because if y is equal to e to the x, then what's y prime? It's also e to the x, right? So if y is e to the x and y prime is e to the x, then this is a solution. So y equals e to the x is a solution to our differential equation. And in fact, we can. It's not the only solution to our differential equation. It turns out that there's an entire family of solutions to this differential equation. Note also 2e to the x also is a solution. If y is equal to 2e to the x, then y prime is equal to 2e to the x as well. So our differential equation actually has infinitely many solutions. And we can state them generally as y equals c times e to the x, where c is a constant. The other obvious example that might jump out as a solution to this differential equation is 0. If y is equal to 0, the derivative of 0 is also 0. This is the case. It lives in the same family as e to the x. It's just a case where the constant is, in fact, 0 itself. So note that differential equations don't have to just be in terms of itself, right? We could also have, so we can also have x in differential equations. For example, this is a kind of boring differential equation, but we could have the differential equation where y prime is equal to x. What's the function whose derivative is equal to x? Well, that's just y is 1/2 x squared plus c. If we take the derivative of 1/2 x squared, we get x. That's just from one of our antiderivative rules, right? And if we take the derivative of a constant, then it just goes away. So anytime that we have something times 1/2 times x squared plus any constant, that function will differentiate to exactly x. The particular type of differential equation that we'll be able to solve in this class is what's called a separable differential equation. So a first order differential equation. So first off, a first order differential equation can be written as y prime is equal to f of x comma y. This notation you guys may not have seen before. It is function notation, but it's a function of two variables rather than one variable. It requires two inputs. However, it still behaves the same as other functions do. It has two inputs, but it should still yield a unique output for every single input. So this is a function of x and y. So for example, y prime is equal to xy. That's xy is a function of x and y. It's x times y, right? And a first order diff eq is separable if it can be written as y prime is equal to f of x times g of y. So in other words, a separable differential equation is one where we can totally separate the variables into two separate functions. One function of x times one function of y. So our example here, y prime is equal to xy, we can rewrite this as, this is y prime is equal to f of x times g of y, where f of x equals x and g of y equals y. In other words, a differential equation is separable if you can consider these two things aren't intertwined in such a way that you can't unseparate them, or you can't separate them from each other. The nice thing about separable differential equations is that they can just be solved by using techniques of integration. Um, you'll notice that one of our examples earlier, this y prime is equal to x, this kind of just looks like we took an antiderivative here, right? Like the integral of x dx is equal to 1/2 x squared plus c. That's just one of our antiderivative rules. And in fact, that's actually what happens here. What we'll do, so a first order, so a separable differential equation
Did you write G of G or G of Y?
that is g of y. The bad handwriting strikes again. So a separable differential equation can be solved by separation, so separating, then integrating. That is, y prime is equal to f of x times g of y. We can rewrite this as dy over dx is equal to f of x times g of y. Then this is 1 over g of y dy is equal to f of x dx, which means that if we integrate both sides, the integral of 1 over g of y dy will be equal to the integral of f of x dx. And this should hand us back, this should hand back some function of y and some function of x. Then solve for y. And you're done. You have your answer. You have your general solution. So let's go back through a couple of our examples and just work them out and see how this comes true. Okay. So let's do our first example. Example, y prime is equal to y. We can rewrite this using Newton notation as dy over dx is equal to y. And then we can pull our dx over to the right side and our y over to the left side. So we have all of our terms with y or dy on the left side and all of our terms with x or dx on the right side. So that gives us 1 over y dy is equal to dx. When I refer to separating, this is what I really mean by separating. Not only the fact that you can write it as f of x, g of y, that means that it can be separated. Separating it is pulling all of the y stuff onto one side times dy, and all of the x stuff onto the other side times dx. So this is separated. Then we can integrate. So the integral of 1 over y dy is ln of the absolute value of y, technically plus a constant. And the integral of 1 dx is just x plus a constant. In general, we're not going to write two separate constants. We're always going to collect our constants on the x side at this step. So we will always collect to a single c on the right-hand side. So this will be ln of the absolute value of y is equal to x plus a constant. Now we need to solve for y. We can do that by doing e to the power of both sides, which tells us that the absolute value of y is equal to e to the x plus c. But again, we're going to play a little fast and loose with constants. This x plus c is the absolute value of y is equal to e to the c times e to the x. But e to the power of c is itself just a constant. So y is equal to c e to the x. Some constant times e to the x. Absolute value still. And then to get rid of this absolute value, we have y is equal to plus or minus c e to the x. But plus or minus c is still just a constant. So we end up with y is equal to c e to the x. C is any real number. Note that at this step here, c was greater than 0 because it was e to the power of something, and e to the power of something has to be positive. But as soon as we slapped in this plus or minus, we were good. Oops. Let's take a look at another example. Let's say that y prime is equal to negative x over y. Some of you guys might remember this specific differential equation, actually. It's the answer that we got when solving a related or an implicit differentiation problem, actually, that dy over dx is equal to negative x over y. And we'll see exactly which implicit differentiation problem it is in just a second. So again, we're going to try to separate, right? So we will have y dy is equal to negative x dx. We can multiply both sides by y and multiply both sides by dx. And then we can integrate both sides. So the integral of y dy is y squared over 2. And the integral of x dx is negative x squared over 2. And we'll put our constant over here on the right-hand side. We could at this point actually solve for we could solve for y, but I think it's actually well, let's go ahead and do that. Note that at this point we can multiply everything by 2, and we get y squared is equal to negative x squared plus c, or y squared plus, or x squared plus y squared. Is equal to c. And this is the equation of a circle centered at 0, 0 with radius square root of c. But if we wanted to just solve for y here, we could rewrite this as y squared equals c minus x squared, multiplying both sides by 2. And then we could take the square root of both sides, giving us that y is equal to plus or minus the square root of c minus x squared. Which is our general solution to our differential equation here. Does anybody have any questions so far? All right. So note, we aren't always looking for a general solution. Sometimes we want a single solution, or the solution to an initial value problem. Or IVP. So an initial value problem tells us that we want the solution. We want the solution that passes through this specific point. And instead of having a solution that has a bunch of different possibilities, it tells us that we want the actual single solution that we are in particular looking for. So for example, we're going to solve the initial value problem. Dy over dx is equal to yx squared, and y of 1 is equal to 2. So here, for an initial value problem, you're given a differential equation, and you're given an initial condition. And you can solve this separable differential equation, then solve for c, then give an actual single function as an answer. Okay. So for instance, so here we can separate our separable differential equation. 1 over y dy is equal to x squared dx. And then we can integrate both sides. So 1 over y di is equal to x squared dx. The integral of 1 over y is the natural log of the absolute value of y. The integral of x squared is x cubed over 3 plus a constant. But now we can actually solve for this constant. We can plug in our number. ln of y is equal to x cubed over 3. So that means that ln of 2 is equal to 1 cubed over 3 plus c. Or in other words, c is equal to the natural log of 2 minus 1/3. So we actually have a value for c here. So we can plug that in. The natural log of the absolute value of y is equal to x cubed over 3 plus the natural log of 2 minus 1/3. And then we need to do e to the power of both sides. So e to the absolute value of ln of the ln of the absolute value of y gives us the absolute value of y is equal to e to the x cubed over 3 plus ln of 2 minus 1/3. Note that we can simplify this out a bit. In particular, I want to rewrite this right-hand side as e to the x cubed minus 1/3 times e to the ln of 2. We could also pull out this negative 1/3 and pull it out as a constant multiple, but it's kind of annoying. It still leaves things a little messy, so I think it's better as sort of the one big fraction up there. E to the ln of 2, however, is very easy to deal with. This is 2 e to the x cubed minus 1/3. And now we have that y is equal to plus or minus 2 e to the x cubed minus 1/3. And we just need to decide now what is our sign here. Is it a positive sign or a negative sign? Well, we can go back up to our initial condition here. Our initial condition was that when we plugged in 1, we should get 2, right? So that tells us that if we plug in 1 for x, so note that plus or minus 2e to the 1 cubed minus 1/3 has to be equal to positive 2. Well, 1 cubed minus 1 is 0, so this is plus or minus 2 times 1. But if that has to equal positive 2, then it can't be negative in front. So our final solution ends up being y equals 2e to the x cubed minus 1/3. That's the function that satisfies this differential equation where it passes through the point y of 1 is equal to 2. Any questions about this example here? All right. I want to take a look at a couple of these in a little bit more context. And one of the important context is that every exponential growth model is actually or decay model for that matter, is actually the solution to a differential equation of this variety. Okay?
I'm sorry, my mic was muted, but my question is, why did x become 1? Or that is when you said it.
What's our initial condition?
Oh, the function is 1. Okay, never mind.
The value we're plugging into the function is 1. And that's, yeah. So normally we have y of x is equal to y, right?
Right.
So that's why we're plugging in 1 there to check to see what our sign should be.
I didn't see that. Alright, good.
Okay. Actually, linear models can also be expressed as solutions to differential equations, but that's a little less interesting. So the hallmark of an exponential growth or decay function is that the rate of change depends on some constant times the current value. Like you can have an exponential equation that doubles every period, right? That would be saying that the rate of change should be some multiple of the current amount, right? So, for example, dy over dx, the rate of change of y with respect to x, is equal to 2 times the current value of y. So if dy dx is equal to 2y, then this is a differential equation that can be solved, right? This is separable. Actually, let's not even say 2y. Let's say ky. Where k is a constant. Then this becomes 1 over y dy is equal to k dx. Which means that after we integrate both sides, ln of the absolute value of y is equal to kx plus a constant. And then this one ends up solving basically the same way that we solved our very first differential equation with e to the x. We'll do e to the power of both sides. We get e to the y, or we get the absolute value of y is equal to e to the kx plus a constant, right? And then we can pass that constant through to be the absolute value of y is equal to e to the c times e to the kx. But since e to the c is constant, we'll replace with just c. So y is equal to plus or minus c e to the kx, which is just, that's our exponential growth model. Y equals c e to the kx. So that PE to the RT model that you would have seen in either algebra or pre-calc, or the CE to the KT, or Y not E to the KT, or whatever version that you've seen, it comes directly from this family of exponential, or this family of differential equations. dy dx is equal to some k times the y function. Similarly, and somewhat more trivially, linear models also do this. With a linear model, the hallmark of a linear model is that the rate of change is constant. So we get that dy over dx is just equal to k. And this one is very, very easy to solve. Dy is equal to the integral of k. The integral of blank dy is equal to the integral of k dx. So y is equal to kx plus a constant. There's your linear model equation, point slope form, or slope intercept form even. Does anybody have any questions with what we've gone through so far? Okay. Let's go ahead and look at a couple of other examples of separable differential equations. And then I think we'll probably call it for today. I have some practice problems for you to work on. So today is a little bit shorter, but that's okay. So, for example, let's find the general solution to where did my example go? I just had it. It disappeared. Oh no. Well, that's a shame. Okay, we'll do this one instead. So here we have something that looks a little bit more complicated than the previous cases. We're still going to be able to apply our exact same principles to solving this. We're going to separate first. So we can pull the dx over to the right to give us 2x dx. And on the left-hand side, we're going to pull this bottom part over, this 3 times 2y plus 5 squared. Dy. Note that we could have actually left the 3 over here on the right-hand side if we had wanted to. We could have left that as like 2/3 x and just had the 2y plus 5 squared over here. I would prefer not to leave fractions if I can. And then we can integrate. So we'll take the integral of both sides here. The right-hand side is pretty straightforward. The integral of 2x is just x squared plus a constant. The right-hand side's a little bit trickier. We can't just do this one straight up. We need to find a way around it. There's really 2 ways we can tackle this integral. But either way, I'm going to sort of bring this off over here to a box. So we're dealing with the integral 3 times 2y plus 5 squared dy. And we can either tackle this by expanding or u sub. The u sub is a pretty straightforward one, so I'm just going to do the u substitution. In this case, our choice of u that works is u equals 2y plus 5. Then du over dy is equal to 2. So du is equal to 2 dy, which means that dy is equal to 1/2 du. We can plug in our substitution here. I'm going to pull this 3 out front. So that'll be u squared times 1/2 du. So that's 3 over 2 times the integral of u squared du. So that'll end up being 3 over 2 times u cubed over 3 plus constant. And the 3's here can cancel, giving us 2y plus 5 cubed over 2. So this we can bring back up here. So we have 2y plus 5 quantity cubed over 2 is equal to x squared plus c. That's so far our solution. Now the last thing we need to do here is actually just solve for y. So we could multiply both sides by 2 to get 2y plus 5 quantity cubed is equal to 2x squared plus c. Again, technically this is 2 times the old constant, but it's still constant, so I'm just going to leave it. And then we are going to cube root both sides. 2y plus 5 is equal to 2x squared plus c with a cube root over it. Now we can't really just combine all of our constants anymore. When I subtract 5 here and get 2y is equal to the cube root of 2x squared plus a constant minus 5, this doesn't get rolled into the constant anymore, because the constant is now inside of this cube root, so I'm not just directly subtracting 5 from it. And similarly, when we divide by 2 here, we can't just roll that into the constant either. So we end up with y is equal to the cube root of 2x squared plus a constant minus 5 divided by 2 is our solution. Does anybody have any questions about this last example we did here? This one kind of accumulated a little bit more of our knowledge. It not only required basic anti-differentiation rules, but it also required us to actually combine that in with U substitution. I guess it didn't require it. You could have done this without U substitution, but it's I think the version that you get without U substitution is actually a lot harder to solve for y, because I think you get a cubic polynomial in terms of y on the left hand side, and then you have to go solve that cubic polynomial for y, so you'd have to factor it, and it's a whole mess. I think it is actually much nicer if you do the U substitution here.
So I have a technical question.
Yes.
So for example, whenever we multiply the constant by 2, right?
Yes.
Is it maybe sometimes useful to keep the 2
To write 2c instead of...
So then we could just maybe if we could get that 2 out of the way, because I don't know, I feel like just dividing constant by 2 would
like
just
if
make
we
more
then had to later divide by 2, the problem is that we're not really
Yeah.
dividing this constant by 2 at the end, right? We're
Well,
dividing the
not
constant
like
by...
in this case, but like
Right.
maybe in the other examples, do you think it would have been making it
Well,
less complex?
if we did 2c and then we turned that into c, and then we had to divide that by 2 later, right? Then we would also still turn that into c.
Oh, okay.
Right? So
Yeah.
it's generally just like sort of the by rules, we generally just absorb everything into our constant that we can, and just keep writing the same c over and over again, just to sort of simplify things. You're not totally wrong. It would be nice. It would be better to be very fastidious about what we were actually doing to our constant, but because it's just some constant when we're doing the general solution, it doesn't matter. However, note that this constant c here that we end up with at the end might be different than the c you received if you had solved for c for a initial value problem, right? So it's not the same c in an initial value problem.
But here's another then question. So for example, what if that constant got multiplied by something what is constant of power of 2, and then can it technically get outside of that square root then? Or I mean cube root?
It would be difficult to get it out of the cube root because it's 2x squared plus c and then the cube root of that. it would not be possible to pull it out of that cube root without it also being dependent on x, which would make it no longer a constant.
Oh, okay, okay. That makes sense.
So, yeah. This is one of those cases where I feel a little. I don't love this being really sort of lackadaisical with the constants in differential equations, but the fact is that it is just so unbelievably common. Like, it's mathematically valid because you're just rolling things into a constant and replacing it with its own constant. It's in a bit of an abusive notation because technically you should be renumbering the constant every time because it's not the same constant that it was last time. When I pull that 2 into the c, it's no longer the same c. It's not the same constant it was before, but since c is sort of an ersatz generalized constant, we just keep using the same c over and over again. But it's just such a common thing in differential equations. Any resource you find for differential equations will do this and basically not mention it at all. So I think that I would be doing a disservice to not mention that this happens.
Okay, cool, cool, cool.
Yeah. Does anybody have any other questions about any of the examples we just worked through? Okay. So with that, I think I'm going to call it for today. I do have some sheets for you guys to work through, and I will definitely be sticking around for a little while to help out. So yeah, come see me if you guys have any questions. This is our second to last official real class where we're learning new things. So next class we're going to talk a little bit about another couple of applications of integrals. I think we're going to do some position, velocity, acceleration stuff. We might look at some of them using differential equations actually. And then we will pretty much call it a semester and review for the final after that. So yeah, good luck, and I will see the bulk of you guys on Tuesday of next week.
Cool. Thanks, man.
Thank you.
Bye.
Where's my